Every couple of months, I see a headline saying that time is an illusion. It's like the recurrence of the headline itself is proof of its claim. Nothing ever changes, people. It's just an illusion. We'll forever be trapped in a time loop in which physicists tell us that time is an illusion. To break out of this loop, I've had a look at the most recent headline-making paper. What do physicists even mean when they say that something is an illusion? I think it's based on an analogy with optical illusions. This, for example, is a famous optical illusion known as the Fraser spiral. It looks like a spiral, but if you inspect it closer, it's actually not. These are concentric circles that just appear to be a spiral. It's an illusion. But that it's an illusion doesn't mean it's not what we see. We do see a spiral. Kind of, if we don't think about it too much. Because once I start thinking about it, it kind of turns my brain into mush. And that's the whole point. That something is an illusion in physics, loosely speaking, means the same. Something looks like one thing, but if you study it closer, it's something else. And thinking about it turns your brain into mush. A good example is the solidity of matter. This desk certainly seems solid, but if we were to look close at it, it'd be mostly empty space. Again, though, that the solidity is an illusion doesn't mean I don't have the experience of it. The experience is totally real. Getting mushy already? If not, here's another example, free will. Many people have the feeling of using something they call free will. That feeling is totally real. Yet if you look closer at it, there's nothing free being willed in the human brain. It's just particles following the laws of nature. Free will is an illusion. Yeah, definitely mushy now. And it's the same when they talk about time. It's that while we certainly have this feeling of time passing, if you look closer at how physics works, there might be no time. It's an illusion. But is it? Well, the reason physicists talk about this so much is that it's rather controversial. You see, in Einstein's general relativity, time is built in at the very basis. Time is a coordinate and it joins with space to space-time. That's what you start from, basically. In quantum physics, on the other hand, time plays a different role from space. You can, for example, measure where a particle is, but not when it is. Both ways of dealing with time make sense on their own, but they don't fit together. Physicists call this the problem of time. Many of them believe that it's the reason why quantum physics and gravity don't want to cooperate and why we still don't have a theory of quantum gravity. The most widely accepted way of reconciling the two is to make time relational. That might sound like physicists wanted to post pics on Instagram, but not so. It means that the passage of time of one object needs to come from its relations with something else. This can reconcile the two notions of time because it can work both in general relativity and in quantum physics. You see, in general relativity, this space-time is all well and good, but we can't actually measure it. No one can measure a time coordinate. That doesn't mean anything. The time that we actually measure comes from clocks. And for a physicist, a clock is anything that recurs in regular intervals. Pendulum swings, heartbeats, headlines proclaiming that the Nobel Prize is outdated, and so on. Doing this for general relativity is straightforward. You just need to calculate the proper time. For quantum mechanics, not so much. Because how do you define a clock in quantum mechanics, and how do you get a time from that? The task is basically that you need to use one set of particles as the clock, and from that you need to extract a variable that you can call time for another system. And this finally brings me to the new paper, because that's what they've done. They've used a clock system in quantum mechanics, a simple type of oscillator, and have shown that one can use that to define time for another system that's entangled with the oscillator. So the link between the two comes from the entanglement. The new thing about this paper is that they've shown that this also continues to work if the other system is large. It's not something that's confined to the microscopic range, and that builds a bridge between quantum mechanics and general relativity. Assuming that this is right, and this is how time in quantum mechanics comes about, does that mean that time is an illusion? Well, In a sense, yes, because it means that fundamentally at the physical basis, there's no time. There are just relations between different things in the universe. Like, it's not that time passes as you watch this video, it's just that the progress bar is correlated with the number of unread emails in your inbox that you really, really want to get to today. Then again, we all know that that was an illusion. Warp drives have been in the news a lot recently because, so the headlines say, we can supposedly detect warp drive signals and that could help us find aliens. Really? I read the paper and I think this requires some clarification. Warp drives could potentially help us travel faster than the speed of light by a clever exploit in Einstein's theory of general relativity. It's that while it takes infinite energy to speed up an object to above the speed of light, this is not the case for space itself. Space itself can deform faster than light. So what you need is fast space that drags an object with it. You need a warped space, hence the warp drive. Warp drives ultimately are solutions of Einstein's theory. What does it mean to be a solution to a theory? Well, you see, Einstein gave us these complicated-looking equations. They relate space and time with the matter and energy in it. For matter and space to be physically possible, it needs to solve these equations. Problem is that these equations are extremely hard to solve. So hard indeed that some people, by which I mean myself, speculate that maybe our need for dark matter and dark energy just comes from our inability to properly solve those equations, but that's another story. This video comes with a quiz that lets you check how much you remember. Physicists have put forward a few solutions that supposedly describe warp drives in the sense that they have an area in the middle where the space is basically flat, where a spaceship could reside. That's called the passenger capsule, and then there's a bubble of sorts around this region where space is very warped, and the entire thing moves. The idea of the new paper is now that if this warp drive suddenly breaks down for whatever reason, some sort of accident on the intergalactic highway, then that'll emit gravitational waves. That isn't so surprising because pretty much everything emits gravitational waves. Waving my hands emits gravitational waves. Just not a lot of them. The more surprising thing is that they claim in the paper that the strain, so the deformation caused by these gravitational waves, would be so large that we'd be able to measure the signal were it to come from anywhere within our galaxy. It's just that the signal isn't in the frequency range of the current gravitational wave interferometers. It's at a few hundred kilohertz, though there are proposals for detectors to measure in that range. That sounds pretty good, so what's not to like? Well, for one thing, warp drives only solve part of the space travel problem because there's still momentum conservation. Warp or not, if you want a spaceship to move in that direction, you need to chuck out stuff the other direction. So you still need a propulsion system. What a warp drive could do for you is that if you chuck out enough stuff, you don't stagnate at the speed of light, but can go beyond that. Unfortunately, all current calculations say that to get that done, you need to chuck out negative energy, which we don't have. Though, as I just said in an earlier video, I think negative energy could actually exist, so this isn't my main issue with the idea. No, my main issue with these headlines is that no one ever mentions that to get any appreciable warp, you need matter that's very, very close to being a black hole. All the articles I've read totally gloss over that. You see, in the paper, they look at a particular example of a warp drive that has a radius of about 1 kilometer. They say cheerfully in a footnote that the Enterprise E of the Star Trek universe is 685.7 meters in length, so it would smugly fit into the warp drive bubble. It seems like a reasonable size. But if you look at the mass that they have to assume for that warp drive, it's about 0.68 times an m with a funny symbol as index. You know what this symbol is? The circle with the dot inside? That's the symbol for the sun. Yes, that's right. Their warp drive has about 2/3 the mass of the sun. Actually, if you compress that much mass into radius with 1 kilometer, that'd be a black hole already. So I assume they've chosen the distribution to just very narrowly prevent it from collapsing. You see, the reason you get a noticeable warp and a noticeable emission from those warp drives is that they are almost black holes. To create such a curvature, you need to compress nuclear matter like that in our sun to about 1/1,000,000th of its current diameter. And this is the major issue I have with warp drives. It's not the negative energy. It's that to do anything useful, they need these huge, unfeasible energy densities. Don't get me wrong, the papers are well and good, and I'm not against studying the mathematics, but the so-called alien search is warping the truth. When my grandmother died, she was blind. Age-related macular degeneration slowly destroys the light-sensitive layer at the back of the eye. It's a heritable condition. My mother has it. I did a genetic test, and I have it too. I probably have 15 or 20 years or so before it starts, which is why I'm very interested in Elon Musk's quest to restore vision in blind people that'll allegedly make them see even better than they previously could. Resolution will be low at first, like early Nintendo graphics, but ultimately may exceed normal human vision. Forget about building particle detectors. I'll find dark matter just by looking. Okay, more seriously, I'm a little skeptical, which is why I was very interested to see a paper that came out just the other week that investigated Elon Musk's claim. Let's have a look. Elon Musk likes the idea of implanting chips into other people's brains, and quite possibly he also likes that it makes a lot of people uncomfortable. His company Neuralink recently made a lot of headlines because it enabled a paralyzed man to play chess merely by thinking.
I love playing chess, and so this is one of the things that y'all have enabled me to do, something that I wasn't able to really do much the last few years, especially not like this. I had to use like a mouse stick and stuff, but now it's all being done with my brain. If y'all can see the cursor moving around the screen, that's all me, y'all. It's pretty cool, huh?
The idea of Musk's bionic eye is to send information from a camera that might be mounted on glasses to electrodes implanted in the visual cortex. Suitably stimulated, that should produce an image without involving any part of the eye. Musk has dubbed that project Blindside. This design goes a big step further from already existing devices called retinal implants. These have been around for about 2 decades and are implanted not onto the brain, but into the eye and work by stimulating the nerves at the back of the eye. The signal either comes from a camera or is an amplification of light that falls into the eye. They do successfully restore a very limited sort of vision. It's generally not great, but anything is better than nothing. Blindside, however, goes a step further by putting the chip onto the brain rather than into the eye. It's supposed to work by cutting away the skin on your head, drilling a hole into the skull, plugging thin wires into the visual cortex, putting the chip into the hole, and sewing the skin back over it. All of this is done by a robot because you don't accidentally want visual information to go into your nose, do you?
There you go. That's the first insertion.
The chip has 96 flexible threads. They contain 32 electrodes each, which makes a total of about 3,000 electrodes. The device is an upgrade over earlier designs in that it has thin flexible contacts coated by a polymer that's supposedly biocompatible and is powered by a battery that can be recharged contactlessly. If you ask me, that's a great improvement over having cables hanging out of your head. In a press conference of sorts from earlier this year, Neuralink shared an image illustrating the resolution of the device that they are currently working on. It's rather grainy dots, as you can see here in this representation of the street image. Now you might say, okay, but look, all you need to do is more wires and that'll get you a higher resolution. Well, Well, this is where the new paper comes in. The authors of the paper say it's not that easy because it's not how visual perception works. It's not like one dot in the visual cortex is one pixel in the image, you see. It's more complicated. They took all that's known about the workings of the visual cortex and created a computer model that shows the approximate image a person would see for different placements of the electrodes. These are examples for the image reconstruction of a cat video from about 2000 electrodes or so. So a little less than Neuralink, but roughly comparable. Yeah, you know, it's not great, but I take it over being blind. The authors of the paper point out, however, that shape recognition isn't as easy as just adding more electrodes. Neurons fire in patterns and in certain sequences to trigger the perception of moving shapes. They say that for the time being, the limitation isn't the number of electrodes, it's that we don't know well enough how neurons give rise to images. They write, our simulations suggest that in the foreseeable future, the perceptual quality of cortical prosthetic devices is likely to be limited by the neurophysiological organization of the visual cortex rather than engineering constraints. In the press release, one of the authors, Ian Fine, is quoted with saying, engineers often think of electrodes as producing pixels, but you can't stimulate 44,000 cells in a blind person and say, draw what you see when I stimulate this cell. Basically, they're saying that Elon Musk's idea of a better than normal human vision is nonsense. Neuralink is of course not the only company working on neural implants. An interesting competition is the US/Australian company Synchron, because they're working on a brain interface that does not require open brain surgery. They instead want to deliver electrodes through blood vessels, and they have completed some very interesting trials. It seems like a good idea to me, because having a hole drilled into my head isn't my idea of a fun afternoon. Something is brewing in quantum computing, people, and this could be a total game changer. It's hard to evaluate the promise of quantum computing because there are so many people who have a reason to exaggerate their research, so much so that sometimes I'm not sure whether they're joking or not.
At D-Wave, my title is the Vice President of Quantum Technology Evangelism.
But I think there's really something going on this time. I have in the past years told you a few times that photonic quantum computing is hot, hot, hot. Just a few weeks ago, I mentioned that the photonic computing company PsiQuantum has attracted substantial new funding and put forward a design plan for a scalable quantum computer that could bring them up to 1 million qubits very quickly. They've partnered up with the microchip manufacturer Global Foundries to get the job done, and just last week I read that they've acquired factory ground near Chicago. These people are clearly very sure that they've got it sorted out. The interesting thing that I want to talk about today is the reason for why this is happening and what that may be doing to the rest of quantum computing. Photonic quantum computing, as the name says, works with photons, the quanta of light. But you see, the issue with photons is that there's no easy way to entangle them once you've created them. You can create them entangled, and physicists do that all the time, but changing the entanglement later is difficult. This is because photons don't interact with each other. Some groups are trying to get this done with nonlinear in medium effects, which is very interesting, but it's complicated. This is why PsiQuantum is using a different approach. The standard approach is called gate-based, and it's very similar to how a conventional computer works. A logical gate is the computer entry point for Bill Gates. Just checking if you're listening. A gate is the part of a computer that performs the logical operations of a computation. You start with your qubits on the quantum computer in a default state, and then you apply operations to them that move the entanglement around. At the very end, you make a measurement, and where you find your qubits, that gives you the answer, or at least that's the idea. The problem is that how well this works depends a lot on how good the gates are. But because that's so difficult to do with photons anyway, the photonic people do it differently. They start with a big state of entangled photons and then use those as the initial state and then just do measurements. It's called measurement-based quantum computing. This has a couple of advantages. Most importantly, you don't have to worry about how good your gates are. It's also easier to make fast measurements in parallel to each other than it is to do gate operations, which gives a speed advantage. And there are some error correction protocols which can be used on the measurement-based approach that don't work on the gate-based approach. If that makes you think now, why hasn't everyone been doing this in the first place? There are probably a lot of people now thinking the exact same thing, because this approach can't just be used for photonic computing, it can also be used for other quantum computers. And you can bet that as we speak, there are quantum computing companies all over the world shifting from the gate-based approach to a measurement-based approach. This can make a dramatic difference very quickly. Will it work? I've no idea. You see, it could just be that they're pushing around the bump under the carpet. If you use a measurement-based approach, you no longer have to swap around all that entanglement with gates, all right, but you still have to create it and get started. And doing that for 1 million qubits might turn out to be very difficult. How difficult? No one knows, because no one's done it. What would it mean if that'd work? Let's do some speculation, because that's the real fun part, isn't it? First and foremost, some people would become very rich very quickly, starting with all the shareholders of photonic computing companies. And some people would lose a lot of money very quickly. That's all the people who have invested into companies who can't pull this off quickly enough, which will be most of them. The second thing that'd happen is that global security concerns over decrypting top secrets would explode. And the third thing is that some banks will up their game by using quantum computing, and whoever is the fastest will make a lot of money before the rest catches up. This could all happen within a couple of years. Now, let me be honest, I still don't really believe it. I think quantum computing is a fine-tuning problem, much like nuclear fusion, and chaos will come back to bite you no matter how you try to get your 1 million qubits sorted out. But what do I know? Maybe I'm wrong, in which case the next few years will be very, very interesting, so don't forget to subscribe. For most scientific research, the purpose is obvious. A cure for cancer, better solar cells, the role of childhood aerobic fitness in successful street crossing. Yes, that's published research. Knowledge that we can make use of. But dark matter? Supposedly it makes up 80% of all matter in the universe. So what? If we can't do anything with it, who cares? Well, since you clicked on a video about dark matter, you probably do care, at least a little bit. So today I have a new paper about a neat experiment that uses the entire planet Jupiter as a dark matter detector. I want to tell you how that works and then why I think that dark matter does matter. Astrophysicists often talk like the existence of dark matter is settled science, but I think this isn't so. They say we have a lot of evidence, but what does this evidence really tell us? It tells us that if we just use all the matter that we have measured on Earth, the stuff that's in the standard model of particle physics, and fill the universe with that, it's just incompatible with observations. Dark matter is one of the ways to fix this discrepancy between observations and predictions. These particles would have to be mostly inert, interact very rarely, and make themselves noticeable primarily by their gravitational pull. An alternative explanation is to change the laws of gravity, or maybe we live in a computer simulation and that's the programmer's sense of humor. But how would you go about confirming that dark matter is really made of these particles? Well, you want them in a detector that goes ping. This should be possible because the dark matter particles, if they exist, which they may not, are supposedly all around us, and Earth is flying through this dark matter soup, basically. It's just that the dark matter particles interact so rarely that we normally don't notice, so you need a very sensitive detector. or a very big one. These dark matter detectors all work more or less the same. You take a big tank or a big chunk of material and monitor that very closely. What you're looking for is the rare interaction of the dark matter particles with that material. It could cause an atom to wiggle and that'd create a very slight heating. Or it might kick an electron into a higher energy orbital, and when the electron drops back down, this emits a photon. Again, you can measure that. Now imagine having a detector the size of planet Jupiter. This is what the new experiment is about. They use data from the Cassini mission, which was actually studying Saturn, not Jupiter. But on the way to Saturn, it made a flyby on Jupiter, because even satellites are better at multitasking than me. On that occasion, it measured what's going on in Jupiter's atmosphere, in particular the infrared emissions in the spectral window between 3 and 5 micrometers. These come from an odd molecule which is hydrogen-3 in the upper parts of the atmosphere. What happens there is that when sunlight falls onto the atmosphere, the ultraviolet light can split some of the hydrogen-2, which then sometimes forms hydrogen-3. This is kind of like in the upper atmosphere of Earth, oxygen-2 gets split and sometimes forms oxygen-3, which is ozone. The hydrogen-3 on Jupiter now, in contrast to most other molecules there, can absorb and emit in the infrared. But you expect this to only happen on the sunny side, by which I mean literally the side in the sun, nothing to do with eggs. You need sunlight because the energy to create those molecules needs to come from somewhere. The researchers then say that the hydrogen-3 could also be created by an interaction from dark matter. And then, since they haven't seen this infrared glow on the dark side, this tells us that there wasn't any dark matter there in appreciable amounts. So what the Jupiter detector does is to rule out many types of dark matter, namely all those which could have caused this infrared radiation, but didn't. It's actually a more sensitive probe than many Earth-based experiments would be. This means that just by analyzing the Jupiter data, they've probably killed a whole bunch of bigger detector designs. Take that, particle physicists. That said, let me tell you why I think dark matter matters. This isn't research that'll lead to practical applications in 10 years or 100 years, and maybe not even 1,000 years. Add some zeros if you feel like it. But if we ever want to become a space-traveling species, and I surely hope we will, we need to understand what's going on out there in the cosmos. We'll need to know whether we have to plow our way through clouds of dark matter, or whether maybe gravity works differently. Yes, that's a long time off, but what's the point of enduring the present if not to make the future better? And sometimes I hope when we finally figure out what dark matter is, we get a cosmic pop-up saying, "Quest completed." Thanks for watching. See you tomorrow.